Good morning, everyone. Thank you so much for being here. And yeah, on behalf of Ellen and myself from EarthWhile Australia, we'd like to welcome you. We'd also like to give our thanks to City of Wanneroo and Switch Your Thinking for allowing us to do this workshop today. We will start by, we'd like to acknowledge the traditional custodians of the land on which we meet today, their elders past, present and emerging. And I guess for all of us here today that I'm assuming we're all on the same lands. Yeah, so if you can just take a moment to pay your respects. So we're going to jump right in. So we'll just bring up the slideshow now. Just one moment. Can everyone see the presentation? If you could perhaps just pop in the chat if you can't see it. Otherwise, we're going to assume that you can. And feel free, please, throughout the whole presentation to either raise your hand if you have a question, or you can put your question in the comment box and we'll answer along the way. We love getting questions, don't we, Ellen?
We do.
So Switch Your Thinking, they are a voluntary collaboration and missions in Perth. And so the City of Wanneroo is part of the Switch Your Thinking group. Sorry. No, sorry. Just trying to, there we go. So these are some of the other cities or councils that are also part of Switch Your Thinking. And yeah, if you're not from the City of Wanneroo and have to be somewhere else and your local government isn't a part of this group, you can feel free to contact them to ask to be part of the Switch Your Thinking group. Put that there. So what is Switch Your Thinking? Basically, they run a whole heap of different workshops every month. Normally, when we do face-to-face presentations, we would have a sheet where you can actually put down your name and contact details if you want to be notified of any of the upcoming events. But given that we're online, you'll need to go to their website, I believe, which I think Georgie's going to pop a link in the chat for you. Yeah, she's done that, so that you can sign up to be part of their contact group. And they'll keep you up to date with a monthly newsletter of what events they have running at the time. So they also do an Energy Smart SMS tip, which you can sign up to be a part of too. And it's been said that they've been able to help reduce people's electricity bills by up to 11%, which is fantastic. So you'll just get a SMS tip and they're just that reminder to help you think of little ways in which you can help save on your energy bills. And they also have a rewards for residents group discount. Yeah. So there's a number of different businesses that are part of that. So you can simply by being part of the Switch Your Thinking councils, then you have access to some of these discounts. So yeah, it's definitely worth checking out.
And we're one of them.
We are. Oh yes, we are one of them. So but by being a part of a Switch Your Thinking council, you get access to 15% off our garden consults. So yeah, worth checking out. There's a few other businesses there, so it'd be great to have a look. And so yeah, basically for more information, just jump on their website and have a look around and see what you can find. Okay, so now we're getting into it. Did you want to take off from here, Ellen?
Sure, thank you. So today we're going to be talking about building healthy soil for climate change. And so you've got a couple of bonuses, I believe, in there with that. So we're also going to be looking at not only how we're going to protect our environment, care for our environment, but grow some healthy veggies and perhaps even save you some money along the way. Our work is underpinned by a quote from David Attenborough, who says that no one will protect what they don't care about and no one will care about things that they haven't experienced. So today we hope to give you that bit more experience of soil microbes and understanding how these tiny weeny little things can actually build on, create some sort of foundation to make our lives so much better. And we also want to, so Bonnie and I are here, and behind the scenes we have Georgie. For those of you who know Georgie, you'll know that she's doing her amazing work behind the scenes for us. So as a bit of an overview here, what we're going to be covering as the challenges, what sort of challenges we're facing. And we're going to then be talking about the soil as a carbon sponge. Carbon sponge?
Sounds interesting.
Not a passion fruit cream one. Then we're going to be talking about marvellous microbes, and they are absolutely amazing. We're going to be talking about how to grow healthy soil for you. And also we have a section on questions and answers, which we'll leave a bit of time for at the end. So as Bonnie said, either raise your hand during the presentation and we'll try and answer it then, or leave it till the end, and we'll have a bit of a chat about that along the way. So we are looking at experiencing hotter and drier days and having more bushfires. And with if we're not experiencing, if we haven't actually experienced those things ourselves, we know that they're happening. Well, we have experienced those things with the summer in Perth, and we've got the floods over us. We've had terrible bushfires both here and across Australia. So the hotter, drier weather is these things are, and there's more extreme events. And these things are actually affecting our water security, our food security, and even our human health in things like infectious diseases and mental health issues. There's all these correlations to what's happening. So you might be thinking at this stage, though, so what's soil got to do with it? Well, increasingly, carbon and water have been removed from the soil and they've entered the atmosphere. Urbanisation, land clearing for agriculture, for our transport systems, for mining, these things have all taken away vegetation that previously was able to provide a cooling effect through the shading and evaporation of the earth. And in that process, so soil in that process, it dries out. It loses some of its lovely crumbly structure that can hold the moisture, and that means that it becomes more fragile. It really does. Yeah, it becomes more fragile, and so it becomes subject to erosion with wind and fire and floods. So you might think fire with erosion, but you think about what happens as fires ravage our bushland. So as the water leaves the soil life suffers. Makes sense, doesn't it? I suffer if I don't have a drink of water. And some dies, some goes dormant, but it stops working effectively. So it's this life that these microbes, this life that we can't even see with our naked eye, that's providing all these services to the plants, to the vegetation. They are cycling nutrients, they're holding moisture in the soil, they're breaking down toxins, they're building soil structure so the roots can get through the soil, and they are helping the plant become disease and pest resistant. So these microbes, these tiny little microbes that are too small to be seen with the naked eye, are integral for our life on Earth. And this microscopic life makes a difference between whether we have got soil or dirt. And we sure want a lot more soil than we want than we want dirt. So we're going to take a look at that life a bit later. The microbes that are so small, we're going to do that a bit later. In the meantime, these graphs. So on your left-hand side, you'll see a graph of the sea surface temperature in the blue, and the the continent surface temperature in orange. And you can see that even though we've had big ups and downs in there, that the overall trend is to a hotter climate or hotter weather. And because it's an overall thing, then we can say that the climate is changing. On the right-hand side, we have a map of Australia, and this one is basically showing that particularly the lower southwest, which I believe has the rainfall has decreased something like 20% since 1910, or even it was maybe even been faster than that. But it's a significant amount. And so you can just imagine with 20% less rainfall, the impact that it's going to have on vegetation. And it has this rolling effect with, as it gets drier, then things aren't growing as much. And so we're not getting as much evaporation. It's getting hotter. It's more subject to bushfires. You can find out more about this information on from the IPCC reports, from CSIRO and the climate, state of the climate in Australia, and there's also a section on Western Australia. So with what's happening then is that these changes in the climate are in part driven by the warming of the planet, and in particular our oceans. So what's happening? How's that happening? Well, the Earth is basically enclosed with a greenhouse, a bit of a greenhouse. This greenhouse is compiled of these of gases. So it's a pretty flexible one. It's not made of plastic, which some people might think there's a fair bit, and there probably is a fair bit of plastic in the air, which isn't going to be helping. But these greenhouse gases are, and I'm sure you've probably heard of these, carbon dioxide, methane, nitrous oxide, and water vapor, would you believe? In Earth's case, so basically what's happening is that you see that the energy from the sun can come through that blanket. It's like a blanket, can come through that blanket, and what hits the Earth, some of it is reflected and some of it goes back out into space. Other of it is basically reflected off the greenhouse gases and stays in closer to the Earth. So we end up with these warmer situations. So some of the water that is released from the soil that we talked about ends up being in the atmosphere. And as the soil dries, the carbon is oxidized, and that also ends up in the atmosphere. So we've got the carbon dioxide. The dry soil that we end up with doesn't effectively support the life of the microbes that eat the methane. And so methane ends up in the atmosphere. And the applied nitrogen that we're putting on the soil doesn't all get used up by the plants, and that gets volatilized and goes into the atmosphere. So, so you can see that all of these things can add up. But water vapor, even though water vapor, it doesn't have the same warming effect as carbon dioxide, methane, and nitrous oxide, it makes up something like nearly 90% of the greenhouse gases. So it's huge.
It's quite surprising. It's not what you would think make up such a large part of it.
I mean, and yes, we certainly still need to be really concerned about carbon dioxide, methane, and nitrous oxide, certainly. But
because of their higher greenhouse warming impact. Yeah.
Oh yeah, yes, because so for 1 unit of carbon dioxide, methane is the equivalent of around about, I think it's 30, thereabouts 28, 30 units of carbon dioxide. So, and 1 unit of nitrous oxide is closer to something like 300 times. So it has this heating capacity that we get there. So it's the water vapor side of things, though, that underpins today's presentation. And it makes up, as I say, a lot of the greenhouse gases. So let's just take a bit of a look at a review of the water cycles. So with the large water cycle, we have the evaporation occurring mainly over the ocean sort of thing. Oops, and then we have it condensing into clouds, and these clouds, sometimes, some of it will rain over the ocean, some of it will go over the land, it falls onto the land, and then it comes and flows back through and back out into the ocean. So it's our large water cycle. And you'll hear of some bits where that's going to get impacted with what we're doing today too. The small water cycle, though, is really important, and that's actually what's affecting a lot of stuff, because in the small water cycle, we're getting this this take up of soil from water from the soil through the plant roots. We know that plant roots suck up the water and they combine it with the carbon dioxide in the air in the presence of sunlight and photosynthesize. So we've got this small this process of the water being pumped through the plants. And this water that gets pumped through the plants has quite a few things to do. It's a bit like the blood in our system, except that our blood doesn't head off when it gets to our heads or anything. Whereas the water vapor in the plants is transpired. The water in the plants is transpired once it's finished doing its job. And that comes out from the stomata, from underneath the leaves. And those molecules, would you believe that? So that goes in to make the clouds again and rain, precipitation. But those molecules are actually a bit heavier than the ones forming from precipitation, from over the evaporation. And so they tend to keep the rain a bit closer to hand. It's pretty amazing, isn't it?
It is, yeah. So the rain falls sooner because it's heavier.
Yes.
Yeah.
Yeah. I didn't know that. I don't know whether you did. So although the water vapor concentration in the atmosphere is said not to be directly affected by human activities, like the burning of fossil fuels, excuse me. Sorry, can we just? Sorry, I just need to cough.
Okay. So we don't have such an impact on the larger water cycle, but we do on the small water cycle.
Yeah, we can.
Yeah.
And so let's do it. Let's try and actually impact so that we're actually keeping that water in the soil so it's not evaporating. And so let's look at the idea of a sponge to actually soak up that water. Yeah, a carbon sponge. So this carbon sponge is something that the Australian microbiologist Walter Yanner really puts forward. And if you think of a dishwashing sponge, I mean, it soaks up the water, it holds the water, and when you squeeze it, it lets the water go. Wouldn't that be great if we could have that in the soil?
It would.
Yeah, so basically for the soil to be able to take up water as the rain falls on it or as water falls on it, and then to be able to hold that water until the plants need it and then release it.
And that releasing part's quite important because we don't want waterlogged soils.
No.
We want the water to be released when it needs to be released.
Yeah, on the plants so they can actually
access it.
Access it. So enhancing this carbon sponge in our soil, as Walter Yanner refers to it, has the potential for bringing back that vapor, the water vapor that's in the atmosphere. So that's what we're wanting to do. And that has direct implications for the emissions of carbon dioxide, for methane, for nitrous oxide as well, would you believe? So microbes, that tiny little life in the soil that play a key role. And these little beauties, they play a huge part in producing this sponge. And Bonnie's going to tell you a bit more about that as we go through. But what about, but we know about this water then, how are we going to remove these other, what's soil got to do with removing or mitigating some of these other greenhouse gases? Well, as far as when we've got a nice, plants have got plenty of access to water that they need, just enough, Goldilocks principle, then the plants are going to be growing very well. And they're going to be photosynthesizing. And in that process of photosynthesizing, they're taking up carbon. So that sort of helps to impact our carbon dioxide. When the soil is nice and crumbly and it's moist, then the little microbes, the methanotrophs that eat methane, do a great job. And so they're actually going to be soaking or eating up the methane that animals are producing. And also because the methane is not only broken down by these methanotrophs, but it's also broken down by sunlight and trees. So the trees are going to be growing better because the soil's better. That's all it. But we're going to get there. And the nitrous oxide also, because these little microbes in the soil, they're actually also going to provide nitrogen for the plants as well. And so we're not going to have that nitrogen volatilization as much of that. So, wow. But it's a carbon sponge. It means we need carbon, doesn't it?
It does.
So 1 gram of carbon, this is going to help you understand why. 1 gram of carbon can hold approximately 8 grams of water. So if you think about that, we can translate that to 1% increase in carbon holds an extra 18 litres of water per square metre in your garden.
I reckon my grass could do with that.
Well, and so then that's water or moisture that's going to be held there for the plants for when they need it. At this point, you might be thinking, well, sort of, so what? Well, okay, well, just think about how much water you could hold on your property. And even though we're not going to go completely into it, I'll just get Georgie to put up, we've got just a link to a calculator tool that you can calculate how much water would fall on your property. This 18 litres per square metre, for those of you who have got bigger properties than a little urban property, that equates to something like 177,000 litres per hectare.
Was it in swimming pools? It's quite a few, isn't it?
It was I think about 6 swimming pools.
Yeah, it's amazing.
Underground. Oh gosh. Yeah. So from there, we'd like to, so you might want to think about then, okay, what's my soil like? Can my soil hold water? Well, we've got a little bit that we'd like you to perhaps try. And this is doing some water infiltration. Oh yeah, some water infiltration testing. And it's something that you might like to try at home. So basically to do that, so we use a stainless steel ring, but you could use something like a bit of poly pipe that's cut, or even a tin can that's cut to put into the ground, so you end up with a bit of surface of water. So you probably
something a bit sturdy too, because you're going to be we bang this into the ground about halfway down.
Yeah, it depends on their soil, isn't it?
Yeah.
It does, yeah. On hard soil, you want something really tough. And then we want you to take the equivalent of 25 millimetres, or in the old school, an inch of water, that's going to cover that by an inch. So an inch of soil is going to be covered, or depth in water. And you can calculate that quite easily. So either Google how to calculate volume, or alternatively just use the formula for calculating volume, which is the radius squared times pi. And so, for instance, in a 6-inch ring, which is like this one, you require 447 millilitres of water, I believe. I'm pretty sure it's 447.
I'll take your word for it.
Pour it in at the same, as you're going to pour it in, set the timer on your stopwatch on your phone, and then time it. Basically, you want it to go into the ground in less than 12 minutes. If it's a bit slower than that, then when you're getting a heavy downpour of rain, then it's going to run off. And if it's just a light downpour, it's likely just to be sitting on the ground and evaporate, and that will be contributing to our water vapor in the air, which we don't particularly want.
It's a nice indicative tool.
It
is
is
an indicator.
Yes, yeah, and of course different times of the year will show you different things, but it's just a fun one too, and something to do with the kids if you've got kids at home, to see what's going on. So having done that, let's just demonstrate this idea a little bit more, as far as it's not how much water that you're going to be putting on your soil it's going to make a difference. It's how much you keep. So if we were in person, we'd bring with us some flour and a piece of bread. So try and imagine this a bit. So we've got some flour down here that's effectively dirt. So where the analogy is that it doesn't have any microbes really in it. And up here, we've got a slice of bread. I realise in this picture, we've got our seed grain bread.
We do.
We often will bring white bread because basically this bit of bread is effectively flour plus some microbes. And in this case yeast. In this case, yeast. So what's going to happen when we rain on this dirt soil, or this dirt here, or this soil with the microbes? So we can see here that where it's rained on the dirt, you can see that it has just, a lot of it's just run off and it's just sitting around it. So we have that runoff. And sometimes it can also take some of that dirt with it as well, so a bit of erosion.
That's right.
But look up here, when we put it on the bread, and usually we put quite a bit more on the bread, don't we?
We do.
Because it holds it. It just holds it because of all those little gaps and pores and things in it that the microbes have created. So it's not how much water you put on your garden or your paddock or how much it rains, it's how much you can keep in your soil that you really wanting to be looking at.
You'll have to take our word for it, but if you were to grab a paddle pop and have a dig around, you would see that in that flour, when you pop your pop stick in, basically that top layer just peels off.
It does. It's
like a skin. Yeah. And so nothing's really penetrated, which if you're thinking about a plant growing in dirt, that plant's really going to struggle to get access to water at its roots where it needs it. Whereas in the bed, when you dig around with your paddle pop stick, you can see that that moisture has gone all the way down to the bottom and it's being held there. You can lift the bread up and there's little to no of that water sitting underneath. So yeah, those plants are going to have access to the moisture in drier spells. And this one was actually a demonstration we came across when we did a Kiss the Ground Soil Advocacy course. And yeah, it's just a fantastic demonstration for really bringing home that notion of when we have the microbes, we're building that structure and the soil becomes like a sponge.
A carbon sponge.
A carbon sponge, yeah. So try that one with your kids. Yeah. That was a great one to have a play with.
And I think the other part I'd like to talk about here too. Oops,
it's gone.
It's gone.
It'll come.
So these little microbes that are so that just our life depends on, they're teeming in the soil. And so in a teaspoon of productive soil, there are more microbes than there are people on Earth. Billions of bacteria, meters and meters of fungi, tens of thousands of protozoa, and hundreds of nematodes. We've introduced some names there that you may or may not be familiar with them. But fungi, bacteria, protozoa, and nematodes, you're going to learn a lot more about those as Bonnie takes you through the information.
But you're going to be able to recognise them shortly.
Yeah. But let's just take a quick look. So these are our bacteria up here. This is what we'll be looking for, bacteria, and this is a form of protozoa, and these are some fungi, and this is a nematode. So of these ones, now Bonnie's going to get you better acquainted with
yes, those. Let's get acquainted. And let's head this way instead. So we're now going to show you how we actually identify these organisms. And we're doing this because we're going to have a look at a live sample a bit further down the track. And we would really like you to be able to see each of the organisms and be able to recognise them, see what they are.
And because of that part from what this David Attenborough says, that when you can see them, then you'll actually get to feel, you'll
get to care for them.
Get to care for them and protect them.
And care for them. Oops, that's all right, we'll go back. So in the same way that, oh dear, sorry folks, challenges of technology. So coming back to this image, you can see we've written here, see the human, you can see the child there, you can see the microscope, and in the background you can see the yogurt bucket. And the way in which we can tell that what these things are that we're looking at is by their shape, their size, and their movement. And obviously in this instance, it's a picture, so you can't easily see movement, but it's the movement of these things that help us identify them. And our microbes are no different. So this image here that we have is bacteria. And we're looking at basically all these little kind of dots, the white dots with an outline, they're the bacteria. And they are so small that, in fact, to see them, we need to be using a microscope and looking at them at 400 times what the naked eye can see. So that gives you a bit of an idea of how small they are. And so I'm going to press play on this now. And this is their movement. So we're talking about size, shape, and movement. They're usually a roundish shape, very small, and their movement's kind of this jiggly, shaking, shimmering kind of look. And this is what helps us tell that it's bacteria.
Because some of the things weren't moving.
Yes, so we've got larger, and these larger coloured pieces here are going to be organic matter. There'll be some minerals. So minerals have a similar colour, and you can see the outline. But yeah, you're not going to see
like a jewel, don't they?
They do, kind of shiny. So bacteria, they ooze this sticky kind of slime. And what that slime does is it acts in gluing together the smallest of particles, your sand, silts and clays, and they're building what effectively are little tiny bricks underground. And this is important because Ellen's been talking about building this soil structure. How do we build this, or how do the microbes build soil structure? Well, this is one of the starting points. The bacteria are building these tiny underground bricks. But if you think about perhaps you're building a house and you've got a slab and a pallet of bricks come and they place it on your slab, they're going to be useful, but they're not quite there yet, are they? They're quite compacted.
Well, they're not going to blow away.
They won't blow away.
Probably won't wash away.
Unlikely, but it's not going to be too easy for air and water to penetrate the pallet of bricks. So we can do better. And that is where, oh, here we go. Let's see that again. Let's press this button. This is where our fungi come in. So here we have some fungi, and going back to being able to identify it, what we're looking for is these long strands here. We're looking for uniform width, so it's the same width the whole way through. There's 3 pieces here, one there, and there's also one in the background there. And they're going to have septa, or these dividing walls. Kind of think of like bamboo. You can see in bamboo, you can see those dividing walls. We're looking for septa indicates it is fungi. Don't all have septa, do they? And flat ends. So, and the other thing, so we're looking for size, shape, and movement. So they're longer than bacteria. Movement, they don't have movement.
No, they don't.
In fact, they have to grow to their food. I'm not sure I'd like to be a fungi if I had to grow to my food. So they're your size, shape, and movement. And so going back now to our analogy about the house pad, we've got our pallet of bricks. Well, fungi puts out these long sticky strands and they effectively act like mortar. So they're going to be tying those bricks together. If we think about bricks and mortar, suddenly now we're having building structures. We've got a house perhaps, or
a castle.
Oh yeah, a castle would be all right. And we've now got doors and windows and passageways. There's space for air and water to flow. We've also got some small rooms and bigger rooms, so smaller microbes can hide from the larger ones that want to predate on them. So this is how we now get our soil structure. The bacteria and fungi are really key in that role. So yeah, hopefully that analogy kind of gives you a picture of how that's working. And not only is air and water going to be able to flow through there, but we're also going to be able to have a bit of a pantry where these nutrients can be stored.
Oh, actually, did we want to talk about nutrients at this stage, or will we come back to that?
Would you, like, you say what's on your mind.
So, I mean, as far as the bacteria, when you saw all those little bacteria, that, you know, that ooze that they put out, they also use that to saddle up to the sand and the silt and the clay and organic matter and actually absorb the nutrients from it. So they break it down and absorb it, but they hold it in their bodies. So it's just something to remember, is that the bacteria hold the nutrients in their bodies,
and fungi,
and the same with fungi. So they're a bit like, as Lowenfels and Lewis say, a bit like bags of fertilizer, and that'll just hold that in your head for a moment.
I'll come back to that one again. So there's 2 main functional types of fungi. We've got mycorrhizal, which is this one here on the left, and we also have saprophytic, or sometimes called saprotropic. And the fungi that we're going to be looking out for today when we come to having a look at a sample is this one on the right, the saprophytic. And so they are both important in providing nutrients to the plants, but they work in different ways. So the mycorrhizal have an association with living roots, and they kind of link up inside the plant's roots and cell walls, and they are able to do an exchange. They provide some nutrients to the plant and in return get what they need from the plant. So these guys will only be found where you've got living roots.
So they won't find them in your compost bin?
Not unless you've got plants growing in your
okay.
Not likely. And in terms of our work, in order to see the mycorrhizal fungi under the microscope, you do actually need to stain it
to be able to identify
it. So what we're looking for is the saprophytic, which feeds on dead and decaying matter. So that's kind of distinguish between the two different types.
The fungi is the thing that that connects those communication systems, isn't it? That often we hear about, and it just plays such an important role in picking up the water and particularly nutrients like calcium and zinc and phosphorus. It's another one that these are really important for. And so does this equate a bit back to the microbes that we saw in the bread, that demonstration that we did?
It does. So we were seeing the fungi is what helps to build those pockets, I guess, where the water and that can be held. It's the bit that's tying together those rooms. So yeah, that analogy, the house really demonstrates how we're going to get our bread soil as opposed to the flour.
Oh, everybody has some flour soil, I think, from time to time, unless you've got you're not living in Perth sands.
Okay, so moving on to protozoa. So in this particular image here, there's a few different types of protozoa. Here we have two types of amoeba. On the left, we've got a testate amoeba. And so if we come back to in terms of identifying shape, size, and movement, the different protozoa have different, actually they all have different shape, size, and movement. But I was
going to say they're a bit, the others are fairly similar, aren't they? You know, the bacteria are all really small and whatever, and the fungi are nice and straight and twig-like. Protozoa,
they are different.
A bit different.
So this one on the left is a testate amoeba, and this one doesn't move, or at least not at a speed in which we notice it. And it's an egg-like shape. It's got this opening here. And what they do is they suck in a piece of organic matter and they pull it or plug in, and then they consume the bacteria on it. So most of our protozoa here are going to be mostly eating bacteria. And this is important because, as Ellen mentioned, the bacteria take up nutrients and they store it in their body. And just like bags of fertilizer may have potential, they're not that useful in your shed. So when the bacteria and fungi hold these nutrients in their body, they're not available to the plants. And so that's where our protozoa come along, and they're going to be consuming the bacteria. They take the nutrients that they need, and then they excrete the rest along with things like hormones and enzymes, and they're now making these nutrients available to the plant in a form that they can take up. So these guys become important in terms of cycling nutrients and making sure our plants get the nutrients that they need. So on the right-hand side here, we've got another amoeba, but this one's called a naked amoeba. And if you can see this egg white-like shape here, and you've got the outline coming around here, this one's missing kind of an outside shell, and they actually change form. So if you watch it long enough, you can sometimes see, we've seen ones that look kind of like this blobby shape here, and then they change their form to almost have like points, like a star, or it looks like a double G to me.
We should put some on our Facebook page or Instagram page.
Yeah, we should. Yeah,
they're really fascinating.
They're so fascinating to see. So these guys move, but you can see that their shape is a lot larger than the bacteria looked at, and they definitely don't look like the fungi.
No.
So hopefully you can all recognize that. Now I'll press play here now. So, did you guys see the big hairy one? These guys are fun to watch. So that one was a ciliate. And again, ciliate larger than the other organisms. They're even larger than the protozoa we see. Their movement's very fast. They tend to move in straight lines, and they're covered in all those hairs or cilia. So they're quite fun to watch. But
in terms of our climate change,
they can be a sign that your soil is anaerobic, is going anaerobic, or has been anaerobic. So we don't want to see too many of them. We saw one or two, perhaps not a problem, but when we're seeing an imbalance, where we're seeing lots of them and not some other things, this can be a problem. And they actually, when they release nitrogen, they release it in a form that goes up into the air, as opposed to staying in the soil, being available for the plants.
Nitrogen gas, the reason why plants can't take up nitrogen gas is that the nitrogen gas is 2 molecules of nitrogen, and it's bonded together so tightly that the plant actually can't break it apart, isn't it? And so when the nitrogen, the ciliates are processing the nitrogen, just release it back into the atmosphere, it's not going to be available to the plants.
but it's not all bad.
No, it's not all bad.
Because
it's
of their
diversity too.
We want diversity, and because of their size, they're larger than the other protozoa. They're going to be helping with that soil structure as well, in making, the tunnel similar to our worms do. They're definitely not as large as worms. You still need a microscope to be able to see them, but they're going to be building those smaller little roads underground. So they have a purpose. And we also had, I wonder if I can play this again, this image, just this round shape here, and you'll see some others about this size kind of zipping about. Up here, these ones to the side. I don't know if you could capture them.
They're fairly fast still, aren't
They are fast. They're our flagellates. So they are larger than bacteria, smaller than a ciliate, and they have a flagella or a whip-like tail. And they move similar to, if you imagined Ellen or myself sitting in a lake in a boat and we only had one oar, what kind of movement are we going to make? We're going to be spinning around in circles. So the flagellates, with their one flagella, they tend to make a similar bumbling type movement. So we have used their size, their shape and their movement to distinguish what these guys are.
They are a little bit trickier when we're looking at them.
But they can be,
yeah, but we'll point them out for sure today.
So hope you guys are keeping these in your mind, so when we have a look at a sample shortly, you'll get to see,
oh, and what they do.
Oh dear, why are we flicking through all of our
I don't know. Can we go back?
All right, so, the last of our organisms, the nematodes. Who has heard of nematodes?
Who loves nematodes?
We love nematodes. We love nematodes. Nematodes can get a bit of a bad rap because there are a small group of them, roughly 5% of the nematode
the
species
yes.
are root feeders. They will eat our roots. But if we
tomatoes and things like that.
Tomatoes, carrots, carrots can be affected. And so if we have an issue with root feeding nematodes, it can be a sign that there's an imbalance in our soil, or perhaps that our plants aren't as healthy as they could be. Fortunately, though, as I said, they only make up 5% of the nematode species, and the rest of them can be really, really beneficial.
Why?
Because we have bacterial feeders, fungal feeders, and we also have predatory nematodes, which will eat other nematodes.
Ooh, even root feeders?
Even the root feeders. We want some of those guys if you've got root feeding nematodes. And they are going to be consuming, because of their size, so these guys are a lot larger than the protozoa we saw and definitely larger than the bacteria. They're going to be consuming a lot of these organisms, and just like the protozoa, they become the spreaders of these nutrients. They're going to be eating the organisms, keeping what they need and excreting the rest and making them available to the plants. So coming to shape, size and movement. In terms of size, these are so much larger than the other organisms that we can often see them using just what's the word I'm looking for? An objective that allows us to see at 40 times what the naked eye can see, as opposed to 400. We can see them, but you still need a microscope to see them. And in terms of their movement, we can come back here now. So you can see that movement. It's very serpentine or snake-like. They kind of wriggle around in the soil. We've got
it's really active, isn't it?
We do. We have a very active one and a less active one there. So we've got the shape, size, and movement. Yeah, the shape's very worm-like, I guess you could say.
So the movement's quite snake-like.
It is, and they're very obvious when you see them. So we've talked about identifying them, how they play a role in both building soil structure and cycling nutrients to our plants. I reckon we might be ready.
And in relation to what we've been talking about with the climate side of things and getting rid of, getting those greenhouse gases out of the atmosphere, then I guess we've also sort of looked at some of that, haven't we?
We have, yeah.
As far as building the structure and things. So
who is ready to have a look at some real stuff? Oh no, before we do that, we're going to do a review. So I was jumping the gun. So just as a review, in the background here, these tiny little dots that we see, they are your bacteria. Small jiggling like movement. Then we have, we've got some fungi here, this long strand. You can see the septa or the dividing walls. Over here, we've got a nematode. which is blurry because of the movement. And here we've also got, this one's likely to be a flagellate because of its size, and the fact that it's blurry tells us it's moving. It's larger than the bacteria, but we've got our protozoa.
Some of them just don't like staying still for the camera,
Don't. So now we can have a look at some real microbes. So just excuse us while we switch our screens around a bit. We're going to bring up our camera that's connected to a microscope that Georgie is looking through. We don't need to go here. All right, now we're going to go to and just share our screen again. There we go.
Ooh.
All right.
Wow. Okay.
So
I didn't expect to see that.
Oh, did you? This is some of your compost.
Yes, this is some compost.
Some compost of Ellen. So can everyone see the bacteria in the background there? So we've got all these spots here jiggling about. Oh, can you see that this faster movement here? So it's a similar size to bacteria. Oh, here's another one. But see how the movement, they're not really staying in the one spot. They're not just jiggling around. It was making quite large movements around a protozoa.
So that's going to be cycling the nutrients.
It will be. So we've got, if we think about the bags and the spreaders, we've got the bacteria, lots of bacteria. We've got a large piece of fungi here. You can see the uniform width. There's some septa here, flat ends. So again, storing nutrients, and we're going to have some soil structure
because it's going to tie the bricks together from that are being produced by things. Wow.
We've seen protozoa, which are going to be eating the bacteria. Oh, there we go. Does anyone remember what this organism is? Here we've got a testate amoeba. It's an egg-like shape. It's not moving.
It's going to be gobbling up lots of bacteria.
It will be. No, I was wondering. There's a bit of movement.
I've got a friend that I'll go to.
Oh, good. Oh, so what else Georgie's going to find here?
Georgie's popping out now to a different magnification. So previously we were just looking at 400 total magnification, and now we're back to 40 times.
Ooh.
Who can recognize this one? Can't see it. Oh,
we can't see
Helen, can you see the screen now? No.
Because it is being shared, isn't it?
I've got it over here.
Yeah.
Is there anyone else having an issue seeing it? You can see it, Katrina.
Yeah. Thanks, Katrina.
Oh, Helen, I apologise that you can't see it.
Yes, I'm not sure what the problem is.
I'll rejoin. Okay,
yeah,
we'll wait for you, Helen.
Yeah. So we'll ask one just to
come back in. Everyone else can see the nematode. Oops.
Where's it gone, Georgie? Where's it gone? Ooh, nematode chase, nematode chase. And
so the way in which I spoke about the different types of feeders, bacterial feeders, fungal, predatory, and root feeding. It's great, Helen.
Terrific.
Glad to hear it. The way in which we can identify what type is by their mouthpiece, if they're kind enough to stay still. So quite often it can be challenging with the movement. Ellen's got a bit of a better eye than I for when they're moving.
This one's a bacterial.
That's because
it was sleeping when I first met it.
That was convenient.
So not sure if you could hear Georgie, but she said when she first came across it, it was sleeping or being inactive at the time. So she was able to tell it was a bacterial feeder. So bacterial feeders tend to have a broad mouth that allows them to kind of vacuum in all the bacteria that they want to consume. The fungal feeders have a spear that you can see inside their mouth, and they shoot the spear out into a piece of fungi and suck out the cytoplasm. It's a gruesome world down there. And then we've got the
look at it go. Yeah, the ladies.
What have I missed?
The
predatory nematodes have a large tooth inside their mouth. I guess it allows them to eat the other nematodes. And then the root feeders are quite obvious because if you have a look, there's kind of a stalk inside their gullet, and then they've got these two round shapes below the stalk. They're very obvious, so we can see or tell if it's a root feeder.
But this stuff, so this one's in a, oh, hang on, I'll just grab it. So this is in a small sample of compost. You might be able to see it there, and we've made up a solution to take that little drop from that we were looking at. But this is compost. So yes, there are more concentration of organisms, but these are the organisms that you find in your soil. It's alive.
It is.
It's just amazing. So like under my block, in my soil, if I was to look at it,
How big's your block?
oh, about 300 square meters. It's only little, but it's more like a couple of kangaroos under there. And so they
Not literally.
not literally, but in the way, effectively the weight of the microbes.
Yeah.
And so for those people who've got, perhaps you've got horses or something, maybe you have 5 acres or an acre, 5 acres or 100 acres, then just imagine just the mass of livestock, of live microbes you've got under your soil doing this work for you. They are providing so many services, and it's one of the reasons why we need to look after them. Georgie, you've done a great job.
Thank you. There's even a little.
Oh, what else have we got?
No, just a test
Testatometer.
A testatometer.
Another testate just down there.
Ah. And did you say there was some rotifers in here or something?
There was some ciliates.
Oh, so
So Ellen, it sounds like Ellen had some ciliates in here too.
and that's probably partly because the sample got a bit waterlogged because I made it up yesterday.
Yeah.
And
Okay. So the sample, the way in which it's been prepared has provided some anaerobic-like conditions that allows these. And so that's actually probably something to mention, that up to 80%.
Larvae. So this one's an insect larvae, just so that you can see something that, different. This is why we love our microscopes. Look at him go. Look, just they hold on to almost with their tail and then just reaching out. Look at that. An accordion shape. Oh, off it goes. This is in our soil. And we're looking at this at what objective, Georgie?
This one is 10.
So we're looking at this at 100 times what we could see with the naked eye. Oh, well, there was fungi then. Sorry, Bonnie, I interrupted you.
That's good. I was just going to say that at any one time, up to 80% of our soil microbes can be dormant. So, quite often when we do consultations for people or assessments, which is a service we offer, people will say, oh, there'll be nothing in my soil is dead. And you'd be surprised. Quite often what they just need is the right conditions in which to wake them up. So we'll go into that, what conditions we need.
Hope you've enjoyed looking at those microbes. We just love it.
Yeah. All right, so we'll go back to our slideshow now. So share a screen, and we want to come back to our PowerPoint. Okay, so now we've seen some real ones. So how do these guys make our soil better? Well, we have spoken about building structures, building soil structure. So we know that particularly the bacteria and the fungi, when we have both these organisms, they're going to be tying together the bricks with the mortar to make our soil structure. And the protozoa and nematodes are also going to be assisting with this. And then moving outside of, I guess the microbes, we've got worms as well. So they're going to be building those tunnels for water and air to flow through. And when we have soil structure, we know that we can hold more water, just like that bread demonstration that we did earlier. So having the structure allows us to better hold the moisture, which then prevents runoff of our soil, and also topsoil being blown away. There's like a massive amount of topsoil, millions of tons of topsoil being lost because it's simply just blowing away. And when we have events such as like
the dust storms.
Creating,
and so that then ties in because of the dust storms. So we're losing that topsoil because the soil's dried out. We talked about with the water vapors sort of in the air instead of in the soil. That's another one of those issues that comes from these changes in our climate, in our weather conditions, these extreme weather conditions, is that if you remember back to the dust storm that hit Melbourne and all the people who were suffering from asthma and the issues that have there.
Yeah.
And of course, yeah, it flows away into the ocean. It doesn't just flow nowhere.
Yeah, it's quite interesting. So the other thing I wanted to talk about here is that these microbes are actually subaquatic. So simply by having the microbes in your soil, having that, they're coated in a film of water, they exist in a film of water. So simply by having microbes, they're going to be increasing our moisture. And microbes are also carbon.
Oh, yeah, they're a lot of carbon, aren't they?
There is. So we know that when we have the carbon, approximately 1 gram of carbon can hold up to approximately 8 grams of moisture.
There's probably going to be quite a lot of microbes in there.
Yeah. So that's how these microbes are going to be assisting with helping us to hold moisture in our soil. And cycling nutrients, we've touched on that as well. So with having these microbes, the bacteria and fungi in particular, taking up the nutrients, holding them in their body, the protozoa and nematodes coming along to eat them, they're going to be helping cycle the nutrients. So just to go into that in a bit more detail, a bacteria has a carbon to nitrogen ratio of approximately 5 to 1. And then a protozoa has a carbon to nitrogen ratio of approximately 20 to 1. So if a protozoa was going to come along and eat their 1, 2, 3, 4 bacteria, they're going to have their 5, 10, 15, 20 units of carbon. If I got that wrong, but they're now going to have 4 units of nitrogen, but they only needed the 1. So they are going to excrete those 3 extra units of nitrogen, and in a way, such a way that that nitrogen is now in a plant available form. The plant's able to take that up. And it's not just carbon to nitrogen, it's carbon to phosphorus, you know, a number of other nutrients. And then the nematodes, they actually have a carbon to nitrogen ratio of something like
100 to 1.
100 to 1. So, and you know, they're large size, they're going to be eating a lot more of those organisms than, say, the protozoa. So you can just see now how all those nutrients are cycling in the soil. It's just amazing, isn't it?
Absolutely. Absolutely.
So why do we actually need this healthy soil? Well, as we've spoken about, there's the water management. So where we're experiencing a drier climate, less rainfall, we really want to be able to hold on to any rain that we capture. We don't want it to run off somewhere else. We don't want it to be evaporating into the sky. We want to hold it in our soil so that our plants are able to access that moisture when they need it.
I remember what I was going to say.
Oh, fantastic.
It's only taken a while. It's just taken a while. But, you know, because we talked about getting that water in the soil so the plants can have it available, but we don't want it waterlogged.
No, we don't.
So what happens? So that water, once it's actually, it sort of percolates through the structure, that nice structure of the soil, until it reaches bedrock. And by that time, it's actually pretty clean. And it runs along the bedrock into springs and the creeks. So if you see a river or a stream or a creek that's actually running clear, then you can think that it's probably got some pretty good soil that the water's traveling through before it gets to that. Where you see rivers running brown, that's often where we find that there isn't that, the soil hasn't got good structure. And so basically the water's carrying the nutrients and the carbon and the organic matter with it.
Yeah.
But yeah.
Yeah, so with that water management, we want to be holding it in our soil and I guess extending the period in which our plants have access to water if we're not having as much rainfall. And it's going to be taking the moisture from the air and getting it into the ground. And then we know as well, when we have healthy soil, we have healthy plants. And when we have healthy plants, their photosynthesis is going to be optimized. And of course, when we're photosynthesizing, we're taking the carbon dioxide out of the air. So healthy plants become a part of that system in managing that climate change, I guess.
Well, because of the transpiration that's happening, the shading, so that we're not getting the heating in. Well, you know yourself, that if we go and stand under a shady tree, then it's going to be cooler than when you're standing out in the sun. And the degrees in the temperature, when people test with one of those infrared sort of thermometers, can be like tens of degrees difference between bare soil and under the shade of a plant.
It was quite shocking when we had a friend that did it. And it was amazing, the difference in the temperature on bare soil.
And also we heard earlier too about that the trees, particularly trees, but trees can actually break down methane. So you've got to be able to grow healthy ones. And I guess if we're healthy too, when we eat healthy plants, that makes us be more willing to look after things.
That's true. That's true. And then we have environmental protection. So all of what we've just spoken about plays into the environmental protection. And I guess a key part we wanted to highlight was minimizing erosion and the nutrient leaching. So a lot of the was it the 2010 reports done on the
Department of Water.
Department of Water did a study and found that a lot of the algal blooms was actually in fact not coming from nutrient runoff from agricultural properties, which is I guess what a lot of people assume, particularly when we mention this study to other audiences, but it was coming from urban blocks. Was it less than 500?
Less than 700.
Less than 700 square meters. And more shocking was the fact that it wasn't synthetic nutrients that are running off. It was actually coming from organic sources, so like your manures and composts. So when we were thinking about this, part of that is that if we don't have that soil structure that we have been talking about, and I think I mentioned that when we have the soil structure, it's almost becomes like a pantry too. It's able to hold on to those nutrients. If we don't have that soil structure, we lose a lot of that nutrients through the soil, and then it's being run off.
But the answer wasn't using synthetics either, because we'll talk about a little bit later why you wouldn't choose to use synthetic fertilizers. So it's more about just how much. But I guess that
how much, how often we're using it, and having a soil that has the capacity to hold those nutrients.
Because when they run off, that's where you get those dead zones. Like in the Gulf of Mexico, clean up with that dead zone. And because when it's running off too, the nutrients into the ocean create an environment then where more little plants, the algae and things, grow fast, and they take in oxygen as well, and so basically they're using up the oxygen. They end up with these dead patches. But also because the oceans have warmed up too, because they've got this extra warmth from the lack of the trees, from the lack of our bread soil, our structure in our soil, losing our moisture.
It's all very interlinked. All very interlinked. Ooh, microbes, nutrients, and plant health. How good does this carrot cake look? So we have touched on how healthy plants can assist with climate change. Let's talk a little bit more now about how microbes affect healthy plants. So we've covered nutrient cycling, how the microbes help to get the nutrients to the plants, but actually plants are so clever in that it's kind of like this exchange that happens. They put out sugars that that attract the microbes, and the microbes then share these nutrients with the plants. And so the plants know as well that different microbes are particularly good at collecting different kinds of nutrients.
Is that something to do with, like, when they do the photosynthesis, that they get their simple sugars? But then the simple sugars, the plant knows that that's not enough. Then add those simple sugars to things like nitrogen and trace elements that are inside the plant. And then it's when they produce things like your complex carbohydrates and your waxes and lipids and proteins.
So if you were to think of these kinds of things like your proteins, fats, sugars, you can be thinking maybe along the lines of butter, oil, sugar, flours, egg. Suddenly, what kinds of things can we make with these ingredients? Cakes, cookies. Oops, I'm just checking the comments here. Was there to see them? Thank you. Oh. Cakes cakes and cookies. These are the kinds of things we're thinking of that are coming to mind. That's all good, Katrina. Sorry, just saw that there was a comment. So these plants can actually change the combinations of these ingredients as such to make different things. So if I knew that Ellen in particular was really great at going and collecting boron, which is something that I feel like right now as a plant, I really need some boron. I also know that Ellen particularly likes carrot cake. So I mix together all of these things and spit out my exudates that have the smell and aroma of carrot cake. And Ellen, who happens to be wandering around in my soil, suddenly goes, carrot cake. And so she comes running over and we do this little trade where I give her some of this carrot cake and she gives me the boron. So the plants are able to do this basically at any time for anything that they need. And they can call in the microbes that they need. And not only is it that different microbes are great at collecting different kinds of nutrients, there's microbes that, for example, there's a microbe that is really good at protecting plants against frost up to
6 degrees.
6 degrees. I was going to say 6 degrees. So, you know, they're kind of like providing the blanket for the plant. And so, yeah, these plants can put out these different sugars to attract what they need.
And there's medicines too.
Medicines too, things to protect them against pest attack. So I guess there's a few key things here. The key thing is we want to have this diversity of microbes in our soil, because when we have diversity, then we have access to different microbes that do all these different jobs.
Because microbes are a bit like people. Well, if we think of them, I guess it's a bit like people. And we are often good at doing different things, or we've got different tools or different contacts and networks. So yes, microbes are a bit like that. So if we've got lots of them, lots of different ones, we can achieve
just about anything. So Ellen likes to talk about if we had this outrageous, audacious goal of building a house in one weekend, we probably couldn't do it on our own. But when we've got lots of different people with lots of different skills, we've got brickies, carpenters, planners, team makers, conflict resolutionists, but suddenly perhaps we have a better chance of getting this house built in the weekend. And this is the same under the soil. We want that diversity of microbes with different skills as well as the quantity of them. And so when we come along and, you know, obviously for people that like gardening, we want to do the right thing by our plants. When we're feeding our plants, and it can be using synthetic or organic means for feeding our plants, what we're basically doing is effectively making our plants lazy. So we're giving them the nutrients that we think that they need when we think they need them. And quite often these nutrients will be enough for our plant to survive. They might even be doing quite okay. But when we're doing this, the plants get lazy. They stop putting out the sugars to get all these other things that they need.
Like getting pizzas delivered or having room service in a hotel.
And so these plants stop putting out the sugars, and then suddenly these microbes are not getting what they need from the plant either. So they may either go dormant, or perhaps they'll disappear to another plant where they can get the sugars that they're after. And what happens then when we suddenly, for a period of time, don't have the means to feed our plants?
Or room service in my room, and I've, you know, like the kitchen, the phone's not working, I can't get through to the kitchen, and I'm really hungry, but there's no food in the pantry. There's no pantry, and I've got nothing to cook with anyway. It's not looking good.
It's not looking good. So the plants lose their ability, I guess, to thrive in that environment. So that's not to say you can't feed your plants, but we talk about little and often. We don't want to be overdoing it. One, because again, going back to these nutrients being leached, if we're overfeeding our plants, you know, we can be causing these microbes to go dormant. We're going to be losing the structure in our soil, which then means that which we do feed, some of it's going to be leached away. But also we want our plants to be able to thrive and survive and thrive even without our inputs. Hopefully that makes some sense. Feel free to jump in with questions if you have any. So the next slide we're going to here is the plant health pyramid. This comes from the work of John Kemp. You can find it on advancingecoag.com. And we recommend people go and have a look on the website. Georgie will add a link for anyone interested, because if you can read that fine text on the side there, I am impressed. But what we want you to see here is that if this plant health pyramid at the top is where we're going to see peak health of the plant, these first two bottom layers up to the top of the blue layer, these can be achieved simply by having balanced chemistry in the soil, the right nutrients for the plant. And when we get to the top of that blue layer, we're unlikely to see pests from whitefly. But if we want to reach the top of this pyramid, and at the top is where we're going to see flavor, aroma, nutrient density in the plant. So, if you're growing your own food, we want to be up the top here. Not only are we going to see these things, we're also going to be seeing a resistance to pest attack and disease. But the key part here is that to reach the top of that pyramid, you need to have vigorous, active biology.
A bit like all those people that are going to build the house. Lots of
Yes,
them.
lots
and
of
lots
them.
of diversity.
And lots of diversity. So yeah, certainly worth a check out if you get the opportunity. So how are we going to support these soil microbes? So you've probably heard quite often we make references to these microbes being similar to people. And the same as us, they need food, which is going to be primarily in the source of carbon, or in the form of carbon, I should say, air and water. So we want our soil to be aerated. They need to have access to water and protection. And in terms of protection, we're talking about protection from the sides, so pesticides, herbicides, nematicides, fungicides. All of these things are going to have an impact on your microbes. Tilling. When we till our soil, we not only are exposing these microbes to the elements, such as air and heat, which is going to have an impact on them, but we may be chopping up the fungi. The fungi is very fragile. We may be breaking into smaller pieces, which can be problematic.
You got it?
Are you going to bring up the fact that I said we want air in the soil?
I'm going to pick up. Yes.
Yes. So I know that's challenging, isn't it? It's a challenge to, on one hand, have aerated soil, but yet not be tilling. One of the things we suggest is perhaps rather than going in and turning all the soil, maybe just with your broad fork or even a pitchfork and just aerating gently. And then also we tend to put down something like worm extract or
humates or compost tea.
Yeah.
But also that bit about the aerobic, because what it actually is that we want our soil overall to be aerobic. So about they say about 25% of the volume of the soil will be air. It's a bit weird, but also for the microbes, some of the really beneficial microbes actually need virtually to be no air or very little air. And so that's where that soil structure comes in again, because in those rooms, there's some big rooms and airy rooms and some small rooms and without much air. That's where those microbes can do their magic. So, but the reason we need lots of the air spaces too is because the roots need air when some of that side. So we need those mixtures. But yeah, that air, the tilling, and it's not really that we're fundamentalists either, is it? So if you need to till, it's just, please don't till every week.
Yeah, I guess we just want you to be mindful of the impact it can have on these microbes. If you feel you must do certain things that you know are going to have an impact on the microbes, then I guess you could perhaps, one, think of what are some alternatives that won't be as harmful, or two, if you have to do it, how can I mitigate this? In the same way that sometimes we might have to take an antibiotic. We don't really want to do this unnecessarily. We might think of, again, alternatives, or in some cases, yeah, you really do need to take an antibiotic and it's going to impact your gut flora. So we would do that, and then we might be thinking about taking pre and probiotics to mitigate the harm we've done. And the last thing I wanted to touch on was synthetic fertilizers. So I guess if you're looking at using synthetic fertilizers, one of the things to look at is that many of them can be salt-based. And if we think about what we can use salt for preserving food, we're going to add salt and it's going to dry out whatever it is we're preserving. And so it has the same impact on our microbes in the soil. It's going to be drying them out.
And so salt isn't just sodium chloride, it's like this phosphates and sulfates and carbonates.
Yeah. And the last one we like to add is friends. And I think we've touched on diversity a bit there. So diversity is really important. Next, sources. So how are we going to get these microbes? So one way is diversity of green plants. We haven't spoken about this, but just as we as a collective, we have our human gut biome. As individuals, we're all going to have slight differences within our gut microbes, and plants are similar. So each plant has its own microbiome. In fact, each seed has its own microbiome within it that's going to help protect them when they germinate. It's really interesting, isn't it?
Yeah, so basically where the seed come from or where the seed was formed is going to have an impact on what sort of microbes are going to be in it.
So this is a great reason to save your own seeds, because the seeds over time are going to become more and more, they're going to contain those microbes that are right for the condition in which they're being grown. But by having this diversity of green plants, when we have a diversity, we're suddenly going to have a diversity of microbes in the soil. And we've spoken about the importance of that. Diversity is just wonderful for looking after our plants. Compost and worm castings are another way in which we can get microbes. With a compost, it's good to be mindful of the different stages of the compost. Can mean that it's more of a inoculant or it's more of a food. And yeah, worm castings are great because not only are we going to have the biology in there, but it's coming with, because of the worms exudates as well, or what they're excreting, is there's going to be hormones and different things in there that are great for our plants. And the last one is commercial products. So there are commercial products out there that come with microbes, and we've had a look at some and can confirm that definitely, you know, when you use them, that it's going to be microbes. But I guess again, being mindful that not all products are going to have the diversity that we're looking for. You're going to be getting a much smaller diversity of microbes. And with all of these things as well, if we're going to be adding microbes in any way, just being mindful that just like us, if you were to pop us out in the Sahara Desert without the things we need to survive, food, water, shelter, we're going to have a pretty tough time. Microbes are the same. So if you're putting it out, make sure you've got the conditions to support them.
And Helen, yeah, we might just go through, we've just got a couple more slides, and then we'll certainly expand on the stage of compost food and whether it's a food or an inoculant.
In fact, we're pretty much just there.
Oh, almost there, are we?
So take us away with our take-home messages, Ellen.
Terrific. So we are experiencing hotter, drier weather. It's definitely the case. And that microbes are essential to store carbon for water management. So that they act as this, microbes act as the plant carbon. They're creating that carbon in the roots, and the microbes themselves, they're creating that structure in our soil so we can hold the water, so we can have our bread soil. They are essential to actually not only, you know, that they actually have the moisture themselves as well. And microbes are essential for healthy soils and healthy plants. If you haven't got the idea that microbes are really important for one thing that leads to another, that can actually help mitigate climate change to some degree, then maybe we haven't done our job. But the healthy soil side of things is actually having that carbon in there. So we've got the balances of moisture and nutrients, that pantry, and so on and so on. So yeah, I think that that sort of hopefully covers why we need this. And I think one of the headline bits on the bit was that things grow from, that soil comes from thin air. And where that comes from is that when plants are growing, the photosynthesis stuff that happens, they're taking carbon dioxide. So from thin air. So if we didn't have that, the plants wouldn't grow. If the plants didn't grow, they wouldn't be putting out the exudates, wouldn't be making the microbes more healthy and building the soil. We wouldn't have all that organic matter happening. But let's get on to your questions. So at this stage, we'll stop sharing.
Yep.
And Georgie, would you like to actually just type in our website, maybe, just so that people can, on our website is a heap of resources. So just go to the resources page to find lots of information. As far as, can you expand on the stage of compost, food and inoculant? Yeah, so basically compost has a lot of different stages. So when it first happens, you're putting all your layers and things in, and action starts to take place. So the bacteria are coming, protozoa then come, you've got your fungi and your nematodes. So often in the early stages, you're going to have more organisms in there. And then as the compost gets more mature, what you're building the compost for there is for the food, for the carbon aspect of things. So most of the composts that you will buy in shops that first up, they've been treated so that they don't have pathogens in them. The other part is that you'll find the level of maturity. And so the older the compost is, in theory, it will have actually more food rather than be able to be used as an inoculant. Does that help? And at this point, please feel free to use the little icon to raise your hand if you've got a question, and then we just ask you to unmute yourself and talk to us, or pop it in the side, whichever. So, Helen, a question you've got?
I was just wondering with what you were just saying there. So do you reckon it's best to use like trench composting where you want to plant later on, and then all the microbes will be there ready, rather than using your compost bin and then taking it out when it's mature?
There's so many different ways to compost, Helen. So what works for you, and in the sense that if you know that you're wanting to plant something in a couple of months or a few months time, then yeah, trench composting is great.
Yeah, and that's actually a method that we did when we because we built our house 11 years ago, and we were working with builder's sand. So we were both composting and just basically burying our scraps. I think we were using a bokashi bucket at the time, so it was semi-fermented, but for us it was just a simple method to do it. And yeah, over time our soils become quite good in our vegetable garden.
So I hope that helps, Helen. And Yanma is asking, can you use worm from the worm farms in the garden bed? Well, if they're particularly a composting worm, then my understanding is that they actually stay towards the surface of the soil, and so there can be a problem when in the hot weather that they can dry. They don't tend to burrow down like more of the indigenous worms do, or the common garden worms do. So you could, but I wouldn't necessarily recommend it. You may be providing organic matter in the way of dead worms for other things to eat. But yeah,
maybe in a shady area
it could
or
be
something. Yeah. Do you know if the introduced worms are problematic for the native worms?
No, I don't. Now there was something I saw, but I don't, Katrina. I'm sorry, that might be a something for somebody to research and find out.
Brilliant.
Yeah, terrific. I recall seeing something recently about, and somebody was doing some research on worms over east somewhere, and they were talking about the impact, and I can't remember whether it was positive or negative. I'd expect that they'd be all something similar, like even with the microbes, that you can if you're bringing in microbes from a completely different area and there's too many of them, then they can upset the balance. Yeah, because we want a balance just as we want the diversity. Any other questions? Oh,
good day.
That's good. So did people find the session useful, and is there something that you might take from the session and do? And it would love if you could just pop it in the chat section there. So has it been useful? And secondly, is there
What
something that
action
you,
are you gonna take?
what action are you going to take? So microbes are just, as you will have seen, have just been so important to all of these different parts. And we actually, they say that we've got a significant number of microbes in our bellies that are the same as in the soil.
Helen's just asking if the recording's going to be available.
So you can convince some other people. Terrific, Helen. And I believe it will be available. Can you recall what the arrangements were for this one?
We'll have to check that one. We're definitely providing it.
We're providing
Link
a link to the
to
City of Wanneroo,
right.
and we'll just need to check.
Check, yeah, whether or not that'll be shareable or to what extent it'll be shareable. How can we get in touch with Helen to let her know?
Okay.
For Wanneroo.
Oh, for the community.
Oh,
Terrific.
lovely.
Yeah. So Helen, if you just like to perhaps email us your email address, then we'll make sure that you get a copy. Yeah.
So I have some work to do to create optimum environment for the microbes to be healthy. And I think the easiest key one is just trying to keep your ground covered. Year-round green cover is going to do wonders in providing an environment good for them.
And I think, Simone, that the thing to remember is that this is a dynamic environment. So even though we might be in optimal health this week, something can happen that will change that next week. And so I guess it's understanding that part of things and being able to think, how can we help to correct things? And so the same with the soil. So I think that I'm sure by the sound of it, you're doing some good stuff.
Good, thanks, Georgie, for popping that in.
Yes.
A few new ideas. Oh, good, Katrina. That's great to hear.
Terrific. And I'm not sure if you've got a microscope yet, Katrina. And I hope that the recording will be available one way or another. Or I'm sure it will be, but we'll just need to let you know. And so we do have we should actually have most of the email. Oh no, because City of Wanneroo have got all your contact details.
Yeah.
Well, good. Well, we might leave it there.
That's exciting.
Terrific. It is exciting. And so I guess on just very quickly then before we go on that, we love this work. We just are passionate about understanding microbes and their role in how they affect our lives. And so we do run workshops for people to learn how to use the microscopes and identify organisms to assess their soil. We do on-site consults, and we also come out and we can do talks with community gardens or arrange an online session like this for a community garden or other community groups. So thank you.
Yes, thank you so much for being here today.
And thanks to Georgie. Thanks to the City of Wanneroo partnering with Richer Thinking for us to be here. We look forward to catching up with you, and certainly touch base with us if you have any questions afterwards.
Lovely.
Thank you.
Thank you.
Appreciate your messages.